Right now, in this very breath, 100 trillion particles are slipping through the hand, resting on the pillow, through the chest, rising and falling, through every quiet thought forming in the mind, and not a single one will pause, or slow, or leave the faintest trace of having passed. These are neutrinos, the ghost particles, born in the hearts of distant stars and in the ancient fire of the sun, traveling at nearly the speed of light across the emptiness of space, only to drift through solid matter as though it were not there at all. They ask nothing of the body. They disturb nothing. They simply continue on their silent way, as they have since the first moments of the universe, indifferent and endless and strangely gentle in their passing. If these quiet hours bring some rest, perhaps consider subscribing so that other still nights might find their way here too. And now, slowly, let us follow the neutrinos into the story of what moves unseen through everything. As you settle into stillness now, letting your body rest against the sheets, feeling the quiet weight of yourself sinking gently into the mattress, something remarkable is happening, though you will never know it through any sense you possess. Right now, in this very moment, as your breath slows and your muscles begin to soften, approximately 100 trillion particles are passing through your body, streaming through you as though you were not there at all, as though the solid matter of your bones and blood and skin were nothing more than empty space, which, in a way that we shall come to understand, it very nearly is. These particles are called neutrinos, and they have been falling through you since the moment you were born, and they will continue falling through you for every second of your life, and you will never feel a single one of them, not one, not ever. And there is something strangely comforting in that, in being so gently and so thoroughly interpenetrated by the universe without the slightest awareness of the passage. 100 trillion is a difficult number to hold in the mind, so perhaps it helps to think of it differently, to imagine each neutrino as a single drop of rain, and then to understand that in the time it takes you to draw a single slow breath, more of these drops will have passed through your body than there are stars in 1,000 galaxies, more than there are grains of sand on all the beaches you have ever walked upon, more than there are seconds in 100 million years. And yet, this rain leaves you perfectly dry, perfectly untouched, because these particles interact so weakly with ordinary matter that nearly all of them pass through the entire Earth without disturbing a single atom, continuing on their journey through the cosmos as though our planet were merely a faint wisp of fog in their path, barely worth noticing, easily traversed. The story of how we came to know about neutrinos begins, as so many stories in physics do, with a puzzle that troubled the sleep of brilliant minds. A small discrepancy in the numbers that refused to go away, no matter how carefully the experiments were performed. In the early decades of the 20th century, physicists were studying a phenomenon called beta decay, in which certain unstable atoms transform themselves by emitting an electron from their nucleus. According to all the laws that were understood at the time, these electrons should have emerged with a precise and predictable energy, the same amount every time, because energy must be conserved, must balance perfectly between what exists before and what exists after. But the electrons did not behave as expected. They emerged with varying energies, sometimes more, sometimes less, and the missing energy seemed to vanish into nothing, to disappear from the universe entirely. which was deeply troubling, because energy is not supposed to simply vanish. It is supposed to go somewhere, to transform into something else, to be accounted for. This missing energy haunted the physics community like a ghost that could not be explained away. Some scientists even began to wonder whether energy conservation might not apply at the atomic scale, whether the rules that governed the falling of apples and the orbits of planets might break down when one looked closely enough at the heart of matter. But there was one physicist who could not accept this possibility, who felt certain that energy must be conserved even in these strange subatomic processes, and who proposed, in December of 1930, a desperate remedy that would eventually reshape our understanding of the universe. Wolfgang Pauli was Austrian, though he spent much of his career in Switzerland and Germany, and he was known among his colleagues for his sharp tongue, his exacting standards, and his physical intuition, which bordered on the uncanny. He was not a man given to speculation without cause, not someone who proposed wild ideas simply for the pleasure of it. And so, when he sat down to write a letter to a conference of physicists meeting in Tübingen, he did so with some reluctance, knowing that what he was about to suggest would sound, even to himself, rather peculiar. He addressed the letter to the gathered radioactive ladies and gentlemen, as was his playful style, and he confessed that he had hit upon what he called a desperate remedy to save the law of energy conservation in beta decay. His proposal was this: that along with the electron, the decaying nucleus also emitted another particle, one that had never been observed, one that carried away the missing energy. This particle, he suggested, must have no electric charge, must have little or no mass, and must interact so weakly with other matter that it could pass through great thicknesses of material without ever being stopped. Pauli called this hypothetical particle the neutron, though that name would soon be given to a different particle entirely, the heavy neutral particle found in atomic nuclei. What Pauli had proposed was something far more elusive, far more ghostly, and he knew it. In the same letter, he expressed his own misgivings about what he had done, lamenting that he had proposed a particle that could never be detected, that he had committed the theoretical sin of inventing something that could not be tested, could not be proven, could not be seen. He felt this was a terrible thing, as indeed it would be if true, because science depends on the ability to check its ideas against the world, to test its proposals with experiments, and a particle that could never be detected would be, in some sense, hence, no different from a particle that did not exist at all. But Pauli need not have worried so much, though he could not have known it at the time, and the particle he proposed would eventually be found, would eventually be confirmed, though it would take more than 2 decades and some of the most sensitive experiments ever devised. In the meantime, the idea was taken up by other physicists, refined and developed into a proper theory, and it was the Italian physicist Enrico Fermi who gave the particle its lasting name. In 1933, Fermi developed a comprehensive theory of beta decay that incorporated Pauli's hypothetical particle, and he called it the neutrino, which in Italian means something like little neutral one, a diminutive term of almost affectionate simplicity for something so profoundly strange. The name distinguished it from the neutron, which had by then been discovered and was known to be a heavy particle residing in the nucleus. And it captured something of the particle's essential character: its smallness, its neutrality, its tendency to slip through the world without making much of a fuss about anything. And so, the neutrino entered the vocabulary of physics, entered the equations and the theories, even though no one had ever seen one, even though Pauli himself still worried that it might be nothing more than a convenient fiction, a mathematical trick to make the numbers come out, right? But the theory worked remarkably well, explaining not only the energy spectrum of beta decay, but other phenomena too. And gradually, the physics community came to accept that neutrinos must be real, must be out there somewhere, streaming through the universe in unimaginable numbers, passing through matter as easily as light passes through glass, leaving no trace of their passage, indifferent to the world of atoms and molecules and living things. Now let us return to you, lying here in the gentle dark, with your body at rest and your mind beginning to drift towards sleep. Consider your skin, the boundary between yourself and the world, that thin envelope of cells that contains everything you think of as you. Every square centimeter of that skin, an area about the size of your smallest fingernail, is being traversed at this very moment by approximately 65 billion solar neutrinos, particles that were created in the nuclear furnace at the heart of the Sun and have traveled across 93 million miles of space to reach you here, in your bed, in this room, at this particular moment in the long history of the cosmos. 65 billion per square centimeter, per second, streaming through you in an invisible torrent that never pauses, never varies much from day to night, never diminishes whether you are indoors or out, because the walls of your home, the roof above your head, the very earth itself, are essentially transparent to neutrinos, offering no more resistance to their passage than a soap bubble offers to a rifle bullet. There is something poetic in the journey these neutrinos have made to reach you, something worth contemplating as you settle deeper into stillness. The neutrinos that are passing through your body right now were born in the core of the Sun, in that unimaginably dense and hot region where hydrogen atoms are being crushed together to form helium, releasing energy in the process. This is the reaction that powers the Sun, that has powered it for 4.5 billion years, that will continue to power it for billions of years to come. And neutrinos are a byproduct of this process, produced in such vast numbers that approximately 2% of the Sun's total energy output is carried away by them, streaming outward in all directions, filling the solar system with an invisible glow that no eye can see but no corner of space can escape. When a neutrino is created in the Sun's core, it does not have to fight its way outward through the dense plasma that surrounds it. Unlike light, which is created in those same nuclear reactions, the neutrino feels almost nothing of the matter it passes through. Light, or rather the photon, which is the particle of light, is constantly absorbed and re-emitted as it tries to make its way from the core to the surface, bouncing from atom to atom in a kind of random walk that takes, on average, 100,000 years to complete. That is not a typographical error, not an exaggeration for effect. A photon created in the center of the Sun today will not reach the surface until 100,000 years from now. So dense is the solar interior, so tortuous the path that light must follow. But the neutrino, created in the same reaction at the same moment, passes straight through all that matter as though it were not there, emerging from the sun's surface in a little over 2 seconds and then sailing through empty space at very nearly the speed of light. 8 minutes later, having crossed the vast gulf between the sun and the earth, having passed through nothing but vacuum and the occasional wisp of solar wind, that neutrino reaches your window, passes through the glass without slowing, passes through the air of your room without noticing, and passes through your body without stopping, continuing on through the earth and out the other side, and then onward into interstellar space, where it will travel for billions of years, perhaps forever, unless by extraordinary chance it happens to interact with some atom somewhere along the way. The light you see, the warmth you feel from the sun, has taken 100,000 years to escape the solar interior and 8 minutes to cross the space between us. But the neutrinos that were created alongside that light, in the very same reactions, have been passing through you for only 8 minutes and a few seconds since their creation, carrying with them information about what is happening in the sun's core right now, or at least as close to right now as the universe allows. And so you find yourself swimming in an invisible ocean, bathed in a rain that never stops, interpenetrated by messengers from the heart of the sun that reach you faster than the light itself, and yet you feel nothing, nothing at all. Your nerves, which are so sensitive to pressure and temperature, which can detect the lightest touch, the faintest warmth, are completely oblivious to this flood of particles, because the neutrinos simply do not interact with the atoms of your body in any way that your biology can register. They do not ionize molecules, do not jostle electrons, do not warm the flesh or cool it. They are there, and they are not there, passing through you in such numbers that the total flux is difficult to comprehend, and yet leaving you entirely unaware of their presence. This is the gentle paradox of the neutrino, the quiet truth that surrounds you always and touches you never, the invisible rain that falls through your body every second of every day, every night, whether you are waking or sleeping, whether you are thinking of it or not. And there is something restful in that, something reassuring in being part of a universe so filled with activity that you cannot perceive, so rich with particles and energies and movements that lie beyond the reach of your senses, streaming through you softly, asking nothing, taking nothing, leaving you exactly as you were, at peace in the dark, drifting gently toward sleep, deep within the heart of our sun, in a place no eye will ever see and no instrument will ever touch directly. There is a furnace of almost unimaginable intensity, and it is here, in this crushing, blazing core, that the particles we are speaking of are born in numbers so vast that the mind finds them difficult to hold. The temperature at the center of the sun reaches approximately 15 million degrees Celsius, which is a figure that sounds extraordinary when you first hear it, and remains extraordinary no matter how many times you consider it, for it represents a heat so far beyond anything we experience on Earth that even our most powerful furnaces and our most energetic explosions are mere whispers in comparison. At this temperature, matter exists in a state called plasma, where atoms have been stripped of their electrons and the bare nuclei of hydrogen, which are simply protons, are flying about with tremendous energy, colliding with one another billions upon billions of times in ways that would be impossible at gentler temperatures. And it is in these collisions, in this relentless atomic dance, that something rather wonderful and rather quiet takes place. For when certain protons manage to overcome their natural electrical repulsion and fuse together, they release energy. And they also, as a gentle byproduct of this process, release neutrinos. The particular sequence of reactions that powers our Sun is called the proton-proton chain, and it is a process that unfolds in several steps, each one leading to the next in an orderly fashion, like a recipe that the Sun has been following for the past 4.5 billion years and will continue to follow for roughly another 5 billion more. In the first step of this chain, two protons collide and fuse to form a nucleus of deuterium, which is a heavier form of hydrogen containing one proton and one neutron. And in this fusion, one of the original protons transforms into a neutron, releasing a positron, and here is the part that matters for our purposes, a neutrino. This neutrino is called an electron neutrino, and it is born with a certain amount of energy that it carries away from the reaction site, energy that will never warm anything, never push anything, never be felt by any material it passes through. The positron, meanwhile, quickly finds an electron, and the two annihilate one another in a tiny flash of gamma radiation. But the neutrino simply departs, moving outward at very nearly the speed of light, beginning a journey that will take it out of the Sun and across the solar system and, in most cases, out into the wider galaxy and beyond, never to interact with anything at all. The Sun produces these neutrinos at a rate that is genuinely staggering when you pause to consider it. For every single second, approximately 2 × 10 to the power of 38 neutrinos are created in that solar core. Written out in full, this number would be a 2 followed by 38 zeros, which is a quantity so large that it exceeds the number of grains of sand on all the beaches of Earth by a factor of trillions upon trillions. These neutrinos stream outward in all directions equally, forming an expanding sphere of ghostly particles that grows larger with every passing moment. And because the Sun is relatively close to us in astronomical terms, a great many of these neutrinos happen to pass through the Earth on their journey. During the daytime, when the Sun is above your horizon, neutrinos are streaming down through the atmosphere and through your body from above. And during the night, when the Sun is below your horizon, they are passing up through the entire bulk of the Earth and then up through your body from below. And in either case, you feel nothing at all, and your body is none the wiser, and the neutrinos continue on their way as if you were not there. The understanding of how the Sun produces its energy, and therefore how it produces its neutrinos, was not always available to us, and there was a time when even the most learned scientists were quite uncertain about what could possibly be making our nearest star shine with such steady brilliance for so many millions and billions of years. It was in the year 1939 that a physicist named Hans Bethe published a paper that would become one of the foundations of modern astrophysics. A paper in which he described, in precise mathematical detail, the nuclear fusion reactions that power stars like our Sun. Bethe was a German-born physicist who had immigrated to the United States, and he was known for his remarkable ability to perform complex calculations with apparent ease, often working out difficult problems in his head or on the backs of envelopes, while others struggled with pencil and paper for hours. His 1939 paper, which was titled Energy Production in Stars, laid out the theory of stellar nucleosynthesis with such clarity and completeness that it remained the definitive account for decades. And it earned him the Nobel Prize in Physics in 1967, nearly 30 years after its publication, a testament to how fundamental and enduring his contribution truly was. There is a rather touching detail about the circumstances under which Bethe worked out some of these calculations, for it is said that he developed much of his understanding of the solar fusion cycle during his honeymoon, which he took in the summer of 1938 following his marriage to Rose Ewald. One can imagine him sitting with his new wife in some pleasant location, perhaps a cafe or a hotel room, scribbling equations on available paper while she read or rested. The two of them beginning their life together while he simultaneously worked out the secret of how the sun produces its light. It is a gentle reminder that great scientific insights do not always emerge from laboratories or universities, that sometimes they come during quieter moments, during vacations or walks or course, in this case, during the early days of a marriage that would last until Bethe's death in 2005 at the age of 98. Rose Bethe, for her part, lived until 2022, reaching the remarkable age of 105. And one wonders whether she ever thought back to those honeymoon days when her husband was explaining to her, or perhaps simply to himself, how the sun manages to shine. If you were to step outside on a clear night and look up at the stars scattered across the sky, you would be looking at thousands of neutrino sources. For every star you can see, and indeed every star you cannot see, is a nuclear furnace much like our sun, each one running its own fusion reactions, and each one producing its own tremendous flood of ghostly particles. The brighter stars, the ones that catch your eye most readily, are often larger and hotter than our sun, and they are fusing hydrogen at rates that far exceed what our modest yellow star can manage, producing correspondingly greater numbers of neutrinos that stream outward into space in all directions. The dimmer stars, the ones you might not notice without looking carefully, are often smaller and cooler, red dwarfs that burn their fuel slowly and steadily, producing fewer neutrinos per second, but continuing to do so for tens or even hundreds of billions of years, far longer than our sun will last. Taken together, all the stars in our galaxy are producing neutrinos at a combined rate that is essentially incomprehensible. A river of invisible particles flowing through the cosmos in every direction, passing through planets and moons and asteroids and dust clouds and, eventually, through you, without any of these encounters making the slightest difference to the neutrinos or to the matter they are passing through. But the sun and other ordinary stars, for all the neutrinos they produce, are not the most prolific sources of these particles. For there is an event in the universe that produces neutrinos in such overwhelming quantities that it makes the output of a normal star seem almost modest by comparison. This event is the supernova, the explosive death of a massive star. And when a supernova occurs, something rather extraordinary happens in terms of energy distribution. We tend to think of supernovae as spectacular light shows, and indeed they are, for a single supernova can briefly outshine an entire galaxy. becoming visible across millions of light years and producing enough light to be seen with the naked eye, even when the exploding star is in a neighboring galaxy. And yet, for all that brilliance, the light from a supernova represents only a tiny fraction of the energy released by the explosion, roughly 1% or even less. The remaining 99% of the energy, the vast majority of what the dying star produces in its final moments, is carried away by neutrinos. This seems almost paradoxical when you first encounter it, for we are accustomed to thinking of light as the primary carrier of energy across space, the thing that warms planets and drives photosynthesis and allows us to see the universe around us. But in the extreme conditions of a supernova, when the core of a massive star collapses under its own gravity and the temperature rises to tens of billions of degrees, neutrinos are produced in such fantastic abundance that they carry away more energy than all the light and all the kinetic energy of the explosion combined. These supernova neutrinos stream outward from the collapsing core, passing through the outer layers of the dying star without difficulty, and they reach observers on Earth hours before the light does. For the light must fight its way out through the expanding debris, while the neutrinos simply pass through as if the matter were not there. In 1987, detectors on Earth recorded a burst of neutrinos from a supernova in the Large Magellanic Cloud, a small galaxy that orbits our own Milky Way, and those few dozen detected particles represented the first observation of neutrinos from beyond our solar system. A gentle knock on our door from an explosion that had occurred 168,000 years earlier. The ability of neutrinos to pass through matter without interacting is so extreme that it requires some effort to appreciate. We are accustomed to things being stopped by solid objects, to light being blocked by walls, to sound being muffled by barriers, to ourselves being unable to walk through closed doors. But neutrinos operate under different rules dictated by the weakness of the force through which they interact with other particles. If you were to construct a wall of solid lead, one of the densest materials available, and you were to make this wall not just a few centimeters thick, not just a few meters thick, but a full light year in depth, which is to say about 9.5 trillion kilometers of solid lead, stretching from here to the nearest stars. And if you were to send a beam of neutrinos through this unimaginably dense barrier, approximately 9 out of every 10 billion neutrinos would interact with the lead in some fashion. The other 9 billion, 999,999,991 neutrinos would pass through that light year of lead without touching a single atom, emerging from the other side as if the lead had been empty space. This means that when neutrinos are passing through the Earth, which is only about 12,700 kilometers in diameter and composed of materials far less dense than lead, they are encountering what amounts to almost nothing at all. The Earth is, to a neutrino, approximately as substantial as a soap bubble is to a rifle bullet, or perhaps even less so. The neutrinos streaming from the Sun pass through our planet without slowing down, without changing direction, without losing any energy, continuing on their way as if the Earth were simply not there. And in a very real physical sense, from the perspective of the neutrino, the Earth is not there, or at least it is so tenuous and so empty and so utterly incapable of impeding the neutrino's progress that it might as well not be there. And so you find yourself, at this very moment, being passed through by billions of these particles every second. Particles born in the heart of the sun, or in the hearts of distant stars, or in the cataclysmic deaths of massive suns long ago. And you feel none of it. And you never will. And there is something strangely peaceful in that thought. That the universe is so full of activity that passes through us and around us without our knowing, without our needing to know, without our being asked to respond or react or even to notice. In the early years of the 1950s, two American physicists named Frederick Rines and Clyde Cowan found themselves contemplating what seemed to many of their colleagues an almost impossible task, which was to detect a particle that had been predicted to exist, but which no one had ever observed directly, a particle so reluctant to interact with ordinary matter that it might pass through the entire Earth without once being deflected or absorbed. And these two men, working together with patience and considerable ingenuity, set about designing an experiment that would eventually succeed in capturing evidence of the neutrino, that ghostly presence which had troubled the dreams of physicists for more than 2 decades since Wolfgang Pauli first proposed its existence. The place they chose for their experiment was the Savannah River site in South Carolina, a facility operated by the United States government for the production of nuclear materials, where several large reactors hummed continuously and produced, as a byproduct of their fission reactions, an enormous flood of neutrinos streaming outward in all directions, invisible and unfelt by the workers who walked the corridors and monitored the dials and gauges of those great machines. Rines and Cowan understood that a nuclear reactor produces neutrinos in staggering quantities, countless billions of them pouring forth every second from the splitting of uranium atoms within the reactor core. And they reasoned that if one positioned a suitable detector near enough to such an intense source, one might just manage to catch the rare occasion when a neutrino deigned to interact with ordinary matter. Their detector was an elegant arrangement of tanks and sensors, built with careful attention to the physics of what they hoped to observe. At the heart of the apparatus sat approximately 400 liters of water. But this was not ordinary water, for it had been mixed with cadmium chloride, a compound chosen for the particular nuclear properties of cadmium atoms, which are remarkably good at capturing certain particles called neutrons. The idea was beautifully simple in its conception, though demanding in its execution. When a neutrino, specifically the type we now call an antineutrino, encountered a proton within the water, there existed a small but real probability that an interaction would occur, transforming the proton into a neutron while simultaneously producing a positron, which is the antimatter counterpart of the electron. The positron, being made of antimatter, would immediately encounter an ordinary electron in the surrounding water, and the two would annihilate one another in a tiny flash of pure energy, producing 2 gamma rays flying off in opposite directions. A fraction of a moment later, the neutron released in the same interaction would wander through the water until it encountered one of the cadmium atoms dissolved there, and upon being captured by the cadmium nucleus, another burst of gamma rays would be emitted. The detector was designed to recognize this distinctive signature, this 1-2 punch of gamma ray signals separated by a characteristic interval of a few millionths of a second. and by looking for this specific pattern against the general background of other radiation events. Rines and Cowan could be reasonably certain that they were witnessing genuine neutrino interactions rather than some other phenomenon masquerading as their quarry. The experiment required patience and meticulous attention to detail, the careful elimination of false signals and background noise, the slow accumulation of data over many months of continuous operation. But in 1956, after years of refinement and repeated measurements, Rines and Cowan were able to announce that they had indeed detected neutrinos, those elusive particles that Pauli had once called undetectable. It was a triumph of experimental physics, a confirmation that the theoretical framework built up over the preceding decades was sound, and it opened the door to an entirely new way of studying the universe. Frederick Rines would eventually receive the Nobel Prize in Physics for this work, though the recognition came remarkably late. In 1995, nearly 40 years after the original discovery, and sadly after his collaborator Clyde Cowan had passed away. For the Nobel Prize is awarded only to the living. In the years that followed the Savannah River experiment, other scientists began to contemplate even more ambitious projects for detecting neutrinos. And among these pioneers was a quiet and persistent American chemist named Raymond Davis Jr., who would dedicate much of his professional life to the study of neutrinos arriving not from nuclear reactors, but from the sun itself. Davis understood that the thermonuclear fusion reactions occurring in the solar core must produce vast quantities of neutrinos as a natural consequence of the processes that generate the sun's energy. And he conceived of an experiment that would attempt to capture some of these solar neutrinos here on Earth, thereby providing a direct window into the nuclear furnace at the heart of our star. The challenge facing Davis was even more daunting than that which had confronted Rines and Cowan, for solar neutrinos are far less numerous at the Earth's surface than the intense beam produced by a nuclear reactor. And moreover, the particular type of neutrino produced in the sun's core required a different detection method altogether. Davis settled upon a chemical approach, using a vast tank filled with an industrial solvent called perchloroethylene, which is the same liquid commonly used in dry cleaning establishments to remove stains from delicate fabrics. This substance was chosen because it contains a high proportion of chlorine atoms, and Davis knew from nuclear physics that when a neutrino of sufficient energy struck a chlorine atom, there existed a tiny probability that the chlorine would be transformed into an atom of argon, a noble gas that could then be extracted from the liquid and counted. The scale of the apparatus was remarkable. Davis and his team installed a tank containing approximately 100,000 gallons of perchloroethylene, roughly 400,000 liters of this pungent industrial fluid, deep within the Homestake gold mine in the Black Hills of South Dakota. The detector was positioned some 4,850 feet below the surface of the Earth, more than a mile of solid rock overhead. And this extraordinary depth was not chosen for convenience, but for necessity. At the surface, our planet is constantly bombarded by cosmic rays, energetic particles raining down from space that produce a bewildering array of secondary particles and radiation when they strike the atmosphere and the ground. This cosmic ray background would utterly swamp any signal from the rare interactions of solar neutrinos, like trying to hear a whisper during a thunderstorm. And so, Davis retreated underground, allowing the overlying rock to serve as a natural shield, absorbing and stopping the cosmic ray particles, while the neutrinos, indifferent to mere rock, passed through unimpeded. The Homestake experiment began collecting data in 1967 and would continue operating for more than 3 decades, a monument to scientific patience and determination. The results were humbling in their sparsity. Despite the enormous volume of the detector, despite the unimaginable numbers of solar neutrinos passing through it every second, Davis and his colleagues captured only about 1 neutrino interaction every 2 days on average. Imagine, if you will, waiting 48 hours for a single atom of argon to appear in that vast tank of cleaning fluid, then carefully extracting it along with a small amount of helium carrier gas, purifying it, and counting the radioactive decays that confirmed its identity. The patience required for such work is difficult to fully appreciate. The willingness to let months and years accumulate while the data slowly, incrementally revealed its secrets. What the Homestake experiment revealed was deeply puzzling and would not be fully explained for decades afterward. Davis consistently measured fewer solar neutrinos than theoretical models of the Sun predicted he should observe, roughly 1/3 to 1/2 the expected number. And this discrepancy became known as the solar neutrino problem. Either the physicists had misunderstood the nuclear processes powering the Sun, or something unexpected was happening to the neutrinos during their 8-minute journey from the solar core to the detector in South Dakota. Raymond Davis would share the Nobel Prize in Physics in 2002 for his contributions to the detection of cosmic neutrinos, recognition that came when he was 87 years old, a testament to both his longevity and the decades required for the full significance of his work to be appreciated. Across the Pacific Ocean, in a remote region of the Japanese Alps, another remarkable neutrino detector took shape during the 1980s in an active zinc mine called the Mozumi Mine. This facility, known as Kamiokande, which was later expanded into the even larger Super Kamiokande, employed a fundamentally different detection strategy than the chemical method used by Davis. The Japanese physicists, led initially by Masatoshi Koshiba, constructed an enormous tank approximately 1,000 meters underground and filled it with 3,000 metric tons of ultra-pure water. Water that had been filtered and purified to a degree almost unimaginable in everyday experience. For any dissolved minerals or suspended particles would interfere with the subtle optical phenomenon that the detector was designed to observe. The walls of this underground chamber were lined with thousands of sensitive light detectors called photomultiplier tubes, each one a glass bulb roughly the size of a beach ball, capable of registering the arrival of individual photons, the fundamental particles of light. The operating principle relied upon a beautiful effect from the physics of moving charges, something called Cherenkov radiation, named after the Russian physicist Pavel Cherenkov, who had characterized it some decades earlier. When a charged particle travels through a transparent medium faster than light travels through that same medium, it produces a faint cone of bluish light, somewhat analogous to the sonic boom produced by an aircraft exceeding the speed of sound in air. In water, light travels at roughly 3/4 the speed it achieves in a vacuum. So, a sufficiently energetic electron or other charged particle can briefly outpace the light around it and generate this characteristic glow. The rare occasions when a neutrino interacted with an atom in the water would sometimes produce a fast-moving electron, and this electron would streak through the tank trailing a cone of Cherenkov light. An eerie blue flash lasting only billionths of a second, but bright enough to trigger the photomultiplier tubes arranged around the chamber walls. By analyzing which tubes detected light and precisely when they did so, physicists could reconstruct the direction from which the original neutrino had arrived, something the Homestake experiment could not determine with its chemical method. This directional information proved crucial, for it allowed the Kamiokande detector to confirm that neutrinos were indeed arriving from the direction of the Sun, and later from other cosmic sources as well. The construction and operation of these deep underground detectors represents one of the more unusual intersections of fundamental physics and industrial engineering, transforming abandoned mines and purpose-built caverns into cathedrals of science dedicated to observing particles that almost never consent to be observed. The descent to such a detector is itself a journey into strangeness, traveling by cage elevator through thousands of feet of rock, arriving in artificial caverns where the air is carefully controlled and filtered, where the humidity and temperature are monitored with exquisite precision, and where the faintest trace of radioactive contamination in the construction materials must be avoided lest it create spurious signals in the sensitive instruments. The blue glow of Cherenkov radiation, captured by those thousands of photomultiplier tubes, carries information about processes occurring in the cores of stars and in the hearts of exploding supernovae, about events unfolding at distances of millions and billions of light-years across the cosmos. It is a gentle light, a whisper of illumination produced only when the universe's shyest particles happen to make their presence known, and it speaks to us of physics occurring under conditions we cannot reproduce in any laboratory on Earth. These experiments, taken together, represent decades of human effort directed at one of the most fundamental questions we might ask about the nature of matter and energy, namely, what particles exist and how do they behave? The men and women who built these detectors, who descended into mines and monitored tanks of cleaning fluid and ultra-pure water, who waited patiently for signals that came only rarely, demonstrated a particular kind of scientific virtue that does not make headlines, but which lies at the heart of how we have come to understand our universe, which is the willingness to pursue difficult questions over the span of entire careers, to accumulate data point by point, and to accept that some answers will come only after many years of patient observation. In the late 1960s, deep beneath the Earth, in a place called Homestake in South Dakota, a physicist named Raymond Davis Jr. began an experiment that would trouble the world of science for 3 decades, and in its troubling, would eventually reveal something beautiful and strange about the nature of neutrinos themselves. The experiment was elegantly simple in its conception, though enormously difficult in its execution, and it involved a tank filled with 100,000 gallons of perchloroethylene, which is a common dry cleaning fluid, placed nearly a mile underground in an old gold mine where the rock above would shield it from the constant rain of cosmic rays that fall upon the surface of the Earth. Davis was searching for neutrinos from the Sun, Those ghostly particles that stream outward from the nuclear furnace at our solar system's center. And he believed, with good reason based on the physics of the time, that he knew approximately how many he should find. The theoretical framework for this expectation came largely from the work of John Bacall, an astrophysicist who had devoted himself to constructing precise mathematical models of the Sun's interior, calculations that traced the nuclear reactions occurring in the solar core with remarkable detail and care. Bacall's models were built upon the foundations of nuclear physics and stellar theory, incorporating everything that was known about how hydrogen fuses into helium under conditions of extreme temperature and pressure. And from these models emerged predictions about the flux of neutrinos that should be streaming outward through the Sun's bulk and across the 93 million miles of space to reach the Earth. The number was quite specific, and Bacall had confidence in his calculations, though he was always careful to acknowledge the uncertainties inherent in any such theoretical work. And he collaborated closely with Davis to ensure that the experiment would be capable of testing these predictions with the necessary sensitivity. The two men formed a partnership that would span decades, a collaboration rooted not only in scientific necessity, but in genuine friendship and mutual respect, with Bacall providing the theoretical targets and Davis constructing the experimental apparatus to hunt for them. They made an unlikely pair in some ways, the theorist working with pencil and paper and eventually computers to model the invisible interior of a star, and the experimentalist working with tanks of cleaning fluid and careful chemistry to capture the faint traces of particles that barely interact with matter at all. Yet their work was deeply intertwined, each depending upon the other, and together they embarked on what would become one of the longest and most puzzling investigations in the history of physics. When Davis first began collecting data in 1968, the results were troubling from the start. The experiment worked by waiting for the rare occasions when a neutrino from the Sun would strike a chlorine atom in the tank and transform it into an atom of radioactive argon, which could then be extracted and counted. The expected rate, based on Bacall's solar models, was that roughly 1.5 atoms of argon should be produced each day in that vast tank of fluid, a number that speaks to just how rarely neutrinos interact with anything at all. But when Davis carefully extracted and counted the argon atoms, painstakingly separating them from the enormous volume of liquid using techniques of extraordinary delicacy, he found only about 1/3 of what the theory predicted, where Bacall's calculations suggested there should be a certain number of neutrino captures. Davis observed far fewer, and this discrepancy was well beyond what could be explained by experimental error or statistical fluctuation. At first, many scientists assumed that something must be wrong with either the experiment or the theoretical models, because the alternative, that we did not understand something fundamental about neutrinos or the Sun, seemed too unsettling to contemplate readily. Some questioned whether Davis's experimental techniques were sufficiently refined, whether perhaps he was losing some of the precious argon atoms during the extraction process, or whether some background contamination was affecting his results in ways he had not accounted for. Others turned their doubts toward Bacall's solar models, suggesting that perhaps our understanding of the Sun's interior was flawed, that the nuclear reaction rates, or the temperature profile, or some other aspect of the calculations might be in error. The standard solar model, as it came to be called, was subjected to intense scrutiny, with theorists probing every assumption and every input parameter, searching for some way to reduce the predicted neutrino flux to match what Davis was actually observing. This period was difficult for both men, who found their work questioned and doubted by colleagues who could not accept that the discrepancy might point to something genuinely new about physics rather than simply an error waiting to be discovered. Barkul later spoke of lying awake at night, wondering if perhaps he had made some mistake, if somewhere in his calculations there was an error that he had overlooked, some flaw in the input physics or some approximation that was not as valid as he had believed. The uncertainty was a burden that he carried for years. The nagging possibility that he might be wrong, that the theoretical framework he had constructed with such care might be leading the entire field astray. Yet, despite these private doubts, both Davis and Barkul maintained publicly that their work was sound, that the experiment was detecting what it was detecting, and the theory was predicting what the best physics of the time allowed it to predict. And if these two things did not agree, then perhaps nature was trying to tell us something we had not yet learned to hear. The mystery deepened as the years passed, and the discrepancy refused to disappear. Davis continued his measurements through the 1970s and 80s, accumulating more and more data, and the result remained stubbornly the same, always about 1/3 of the expected flux, never coming into agreement with theory despite all efforts to resolve the puzzle. Other experiments eventually joined the search, using different detection methods and different target materials, and they too found fewer solar neutrinos than expected, though the precise deficit varied depending on which types of solar neutrinos each experiment was sensitive to. The solar neutrino problem, as it came to be known, settled into the scientific literature as one of the great unsolved mysteries of physics, a puzzle that touched upon our understanding of both particle physics and stellar astrophysics, and that resisted all conventional explanations. What made the problem so vexing was that it seemed to require something to be wrong, either with our models of the sun or with our understanding of neutrinos themselves, and neither option was comfortable. If the solar models were wrong, then we did not understand the basic physics of how stars work, which would have profound implications for all of astrophysics, for our theories of stellar evolution and nuclear synthesis, and the ages of stars and galaxies. If something was happening to the neutrinos themselves during their journey from the Sun to the Earth, then we did not understand the fundamental properties of these particles, which would require an extension or modification of the standard model of particle physics. Either way, something important was at stake, and the stakes only grew higher as the problem persisted year after year without resolution. There was, however, a possible explanation that had been proposed long before Davis even began his experiment, an idea put forward in 1957 by a brilliant and somewhat unconventional physicist named Bruno Pontecorvo. Born in Italy and later working in the Soviet Union, Pontecorvo had suggested that neutrinos might have the remarkable ability to transform from one type to another as they travel through space, a phenomenon that came to be called neutrino oscillation. At the time, only one type of neutrino was known to exist, the electron neutrino, which is produced in beta decay and in the nuclear reactions that power the Sun. But Pontecorvo speculated that if there were other types of neutrinos, and if neutrinos had even a tiny amount of mass, then quantum mechanical effects could cause them to oscillate between these different types as they propagated, periodically changing their identity in a way that would make them invisible to detectors designed to see only one particular type. This idea was ahead of its time, and for many years it remained a theoretical curiosity rather than a serious contender for solving experimental puzzles. But as the solar neutrino problem persisted, and as other types of neutrinos were discovered, Pontecorvo's proposal began to seem more and more relevant. The muon neutrino was discovered in 1962, produced in the decays of particles called pions and muons, and it was clearly distinct from the electron neutrino that had been known before. Later, in 2000, the tau neutrino was finally directly observed, associated with the heavy tau particle that had been discovered in the 1970s. These three types, or flavors as physicists call them, electron neutrino and muon neutrino and tau neutrino, each paired with its corresponding charged particle, constitute the complete family of neutrinos in the Standard Model, and the possibility that neutrinos might oscillate between these flavors offered a potential solution to the missing neutrino mystery. The logic was beautifully simple once one accepted the premise of oscillation. The nuclear reactions in the Sun's core produce only electron neutrinos, because the reactions involve electrons and their antimatter partners, and Bahcul's models correctly predicted how many of these electron neutrinos should be created. But if, during the 8 minutes it takes for these neutrinos to travel from the Sun to the Earth, some fraction of them oscillate into muon neutrinos or tau neutrinos, then a detector like Davis's, which was specifically designed to detect only electron neutrinos, would see fewer than expected. The neutrinos would not be missing at all, merely transformed into a different type that slipped past the detector unnoticed, like guests arriving at a party in disguises that the host does not recognize. The total number of neutrinos would be exactly what Bahcul predicted, but only 1/3 of them would still be electron neutrinos by the time they reach the Earth. And this 1/3 was precisely what Davis was detecting. For this explanation to work, however, neutrinos would need to have mass, because the quantum mechanical mathematics of oscillation requires that the different neutrino types have slightly different masses, and the Standard Model of particle physics, as originally formulated, assumed that neutrinos were massless. This was not a minor detail, but a significant departure from established theory, and it meant that confirming neutrino oscillation would represent a genuine discovery of new physics, an extension of our fundamental understanding of the universe. The idea was tantalizing but unproven, and throughout the 1980s and 90s, the solar neutrino problem remained officially unsolved, a gap in our knowledge that troubled those who thought deeply about it, and that Bahcul, in particular, returned to again and again in his research. Davis and Bahcul continued their work through all these years of uncertainty, never giving up on the problem and never allowing the doubts of others to shake their conviction that the measurements and the theory were both essentially correct. Their friendship sustained them through the long wait for resolution, through the conferences where skeptics questioned their results, and the journal articles where alternative explanations were proposed and debated. They trusted in the scientific process, believing that eventually, with better experiments and deeper theoretical understanding, the truth would emerge. And they were patient in a way that science sometimes demands, but that human nature finds difficult to sustain. Bacall would later describe this period as one of the most challenging of his career. The years of not knowing whether he was right or wrong, of defending his work while privately wrestling with the possibility of error, of waiting for nature to reveal what it had been hiding all along. The resolution would eventually come, not from the Homestake mine, but from other experiments around the world. And when it came, it would vindicate both Davis and Bacall completely, proving that the solar neutrinos were not missing but merely changed, transformed by oscillation into types that earlier experiments could not see. But that confirmation lay in the future. Beyond the decades of patient observation and careful calculation, beyond the sleepless nights and the nagging doubts, in experiments that were still being designed and built as Davis counted his argon atoms and Bacall refined his solar models. For now, in the telling of this story, we pause at the mystery itself, at the 30 years when physics confronted a puzzle it could not solve, when the sun seemed to be telling us something we did not yet have the language to understand. And so we come now to a quieter kind of revolution, the sort that unfolds not with fanfare, but with the patient accumulation of evidence, the slow turning of minds toward an unexpected truth. And we find ourselves in Japan in the year 1998, where deep beneath a mountain called Ikanoyama, in the clear water of a tank the size of a cathedral, particles from the sky were about to reveal one of nature's strangest secrets. A secret that had been hiding in plain sight for decades, waiting only for instruments sensitive enough and physicists patient enough to coax it into the light. The Super Kamiokande detector, which the scientists who worked there often called simply Super K, was at the time the largest and most sensitive neutrino observatory ever constructed. And it sat more than 1,000 meters below the surface of the Earth, shielded from the constant rain of cosmic rays by the weight of rock and soil above. And within its vast cylindrical chamber, which measured 40 meters in diameter and 40 meters in height, there rested 50,000 tons of water, so pure that it appeared almost supernaturally clear. And around the walls of this chamber, gazing inward like the compound eyes of some enormous and contemplative creature, were arranged 11,000 photomultiplier tubes, each one exquisitely sensitive to the faint blue glow of Cherenkov radiation that would appear whenever a neutrino, in one of its rare moments of interaction, disturbed the stillness of that underground sea. The man who would eventually stand before the world and announce what Super Kamiokande had found was a physicist named Takaaki Kajita, a quiet and meticulous scientist who had been studying neutrinos for many years and who approached his data with the kind of careful skepticism that good science requires. And what he and his colleagues had been doing was watching for neutrinos that came not from the sun, but from the Earth's atmosphere, created when cosmic rays struck the upper reaches of the air and produced showers of particles that decayed into neutrinos as they fell. And these atmospheric neutrinos arrived at the detector from all directions, some coming down from directly overhead and traveling only a short distance through the atmosphere, others coming up from below, having passed entirely through the body of the Earth after being created on the opposite side of the planet, And it was this difference in distance traveled that would prove to be the key. If neutrinos were simple and unchanging particles, as the standard model of physics had long assumed, then they should arrive at super-Kamiokande in predictable ratios, regardless of where they came from. And yet, as the months of data accumulated and the physicists performed their careful analyses, a pattern emerged that did not fit this expectation at all. For the muon neutrinos that came from far away, having traveled through the Earth and crossed perhaps 12,000 kilometers to reach the detector, were significantly fewer in number than those that came from directly above. And this deficit was not a small statistical fluctuation or an error in the instruments, but a clear and unmistakable signal that something was happening to the neutrinos as they traveled. That distance itself was transforming them in some fundamental way. In June of 1998, at a conference in Takayama, Japan, Kajita presented the evidence to an audience of physicists from around the world. And what he described was something that had been theorized for decades but never before observed with such clarity. For the muon neutrinos were not simply disappearing as they crossed the Earth, but were changing their identity, transforming into a different flavor of neutrino that super-Kamiokande was less able to detect. And this process, this strange and dreamlike ability of neutrinos to shift from one type to another as they travel through space, came to be known as neutrino oscillation, a term that captures something of the wave-like nature of the phenomenon. The way that a neutrino's identity ripples and changes according to rules that are entirely determined by quantum mechanics. To understand what oscillation means, we must think for a moment about what a neutrino actually is. Or rather, about the curious fact that this question has more than one answer, depending on how you choose to look at it. For there are two different ways of describing neutrino types, and they do not quite align with one another. And one way describes what physicists call flavor states, which are the electron neutrino, the muon neutrino, and the tau neutrino, named for the charged particles they interact with. And these are the neutrinos that are created and detected in experiments. The identities that appear when a neutrino interacts with matter. But there is another set of states called mass states, each one having a slightly different mass. And these are the true traveling states, the forms in which neutrinos move through space. And the key insight is that flavor states are not the same as mass states, but are rather superpositions of them, quantum mixtures that contain a bit of each mass state blended together. And as a neutrino travels, the different mass components of this mixture evolve at slightly different rates, causing the blend to change, causing the probability of finding one flavor or another to rise and fall like a gentle wave. And so, an electron neutrino created in the heart of the Sun may become, by the time it reaches the Earth, partly a muon neutrino or partly a tau neutrino, not through any violent transformation, but simply through the quiet accumulation of quantum phase. And here at last was the solution to the solar neutrino problem. The mystery that had puzzled physicists since Raymond Davis first counted far too few neutrinos arriving from the Sun. For his detector in the home state gold mine had been sensitive only to electron neutrinos, built specifically to capture that one flavor. And if the electron neutrinos produced in the solar core were changing their identities during the long journey to Earth, becoming muon and tau neutrinos that passed through his tank of cleaning fluid without a trace, Then the deficit, he observed, was not a failure of the experiment or a flaw in our understanding of the sun, but simply the natural consequence of a phenomenon that no one had yet been able to confirm, and what had seemed like a crisis in physics was revealed to be a window into deeper truth. But the story does not end in Japan. For even as Superchemi Okande was revealing the oscillation of atmospheric neutrinos, another observatory was being prepared far away in Canada, buried 2 kilometers beneath the surface of the Earth in an active nickel mine near the town of Sudbury in Ontario. And this observatory, called the Sudbury Neutrino Observatory, or simply SNO, was designed with a specific purpose in mind: to settle once and for all the question of whether solar neutrinos were truly oscillating or whether something else entirely was responsible for the deficit that Davis had observed. The man who led this effort was Arthur MacDonald, a Canadian physicist with a gentle manner and a deep commitment to careful measurement. And the detector he and his colleagues built was unlike any that had come before, for at its heart was a sphere 12 meters in diameter made of transparent acrylic, and within this sphere were contained 1,000 metric tons of heavy water. Water in which the ordinary hydrogen atoms had been replaced by deuterium, a heavier isotope of hydrogen whose nucleus contains not just a proton, but a proton and a neutron bound together. And this heavy water was not ordinary material that could be purchased from a supplier, but rather a precious resource borrowed from the Canadian government's nuclear program. A loan of substance worth approximately $300 million, handled with extraordinary care and eventually returned after the experiment was complete. The genius of using heavy water lay in the way it could detect neutrinos, for the deuterium nuclei within it could interact with neutrinos through not just one, but 3 different processes. And one of these processes, called the charged current interaction, was sensitive only to electron neutrinos, while another, called the neutral current interaction, was sensitive to all 3 flavors equally: electron and muon and tau, and this meant that the Sudbury Neutrino Observatory could measure both the number of electron neutrinos arriving from the Sun and the total number of neutrinos of all types. And if the total matched the predictions of solar models while the electron neutrino count fell short, then the case for oscillation would be closed. The results, announced in 2001 and refined over the following years, were exactly what the theory of oscillation predicted. For the electron-neutrino flux measured by the charged current interaction was only about 1/3 of what solar models expected, consistent with what Davis had seen decades earlier. But the total flux measured by the neutral current interaction was precisely what the Sun should produce. Every neutrino accounted for, none missing, and this demonstrated beyond reasonable doubt that the electron neutrinos born in the solar core were indeed changing their flavor as they traveled, that roughly 2/3 of them were arriving at Earth as muon or tau neutrinos, invisible to detectors like Davis's, but perfectly visible to the all-seeing eye of SNO. For this work, Takaaki Kajita and Arthur MacDonald were awarded the Nobel Prize in Physics in the year 2015, recognized for their discoveries concerning neutrino oscillation, which show that neutrinos have mass, and this final phrase, which may seem like a technical detail, carried implications that reached far beyond the neutrino itself. For the original formulation of the standard model of particle physics had assumed that neutrinos were massless, that they traveled at the speed of light and could never change their flavor. And the discovery of oscillation proved this assumption wrong. For oscillation can only occur if the different mass states of the neutrino have different masses, which is to say, if neutrinos have any mass at all. And so, the existence of oscillation was simultaneously proof that our best theory of particle physics was incomplete, that there was new physics waiting to be discovered, that the Standard Model, for all its triumphs, did not contain the whole truth. And yet, there is a sadness woven through this story. For among those who did not live to see these confirmations was Bruno Pontecorvo, the brilliant and troubled physicist who had first proposed, back in 1957, that neutrinos might be able to change from one type to another, who had spent the latter half of his life in the Soviet Union, far from the mainstream of Western physics, and who had continued to refine and advocate for his oscillation hypothesis, even as many of his colleagues doubted it. And Pontecorvo died in Dubna, Russia, in September of 1993, just 5 years before Kajita's announcement, just 8 years before McDonald's confirmation, never knowing for certain that his great theoretical insight would be proven correct, that his particles would indeed be found to change their minds. It is a melancholy thought, but perhaps not entirely a tragic one, for Pontecorvo had the satisfaction of seeing the solar neutrino problem persist and deepen over the decades, had the quiet confidence that comes from having a theory that explains the data when no other theory can. And in the end, his ideas were vindicated, even if he was not there to receive the applause. And his name remains attached to the phenomenon he predicted, spoken in laboratories and lecture halls around the world. A small immortality of the sort that physics occasionally grants to those who see further than their contemporaries. And so the neutrinos continue their gentle oscillations, changing their flavors as they travel across the vast distances of space, arriving at our planet in all three types, passing through our bodies and our detectors and the very rock of the Earth. And we, having learned at last that they carry mass and that they transform as they travel, have glimpsed something of the deeper structure of nature, something that was hidden for so long and revealed only through the patient work of many hands and many minds. And the story, as such stories always do, continues, for there is still much we do not know, still questions about the exact masses of the neutrinos and the precise nature of their oscillations. And somewhere, perhaps, another physicist is even now preparing the next experiment, the next observation, the next quiet revolution that will deepen our understanding of these most elusive of particles. But that, as they say, is a matter for another time. And for now, we may simply rest in the knowledge that the universe is stranger and more beautiful than we once imagined, and that even the smallest and most ghostly particles can change their minds as they drift through the endless dark. Deep beneath the Antarctic ice, in one of the most remote and inhospitable places on the surface of our planet, there exists an instrument of such extraordinary scale and such patient ambition that it transforms the frozen darkness itself into a kind of eye, an eye that gazes not upward at the stars as we might expect, but downward through the body of the Earth, waiting for messengers that have traveled distances so vast that the very concept of distance begins to lose its ordinary meaning. This is the Ice Cube Neutrino Observatory, and it sits at the geographic South Pole, where the winter darkness lasts for months and the temperatures fall so far below freezing that the air itself seems to crystallize. And yet, within this frozen stillness, within this cathedral of ice that has accumulated over hundreds of thousands of years, scientists have constructed one of the most remarkable scientific instruments ever conceived. A detector that occupies not a room or a building, but an entire cubic kilometer of glacial ice. 1 billion cubic meters of frozen water transformed into a telescope for particles that barely interact with matter at all. The construction of IceCube required years of careful drilling and patient installation, as engineers lowered long strings of sensitive equipment deep into the Antarctic ice sheet, melting narrow channels with hot water and then allowing them to refreeze around cables studded with optical sensors. Each one a sphere of glass containing delicate electronics designed to detect the faintest flickers of blue light. There are 5,160 of these digital optical modules frozen into the ice, arranged in a three-dimensional grid that extends from 1.5 kilometers beneath the surface down to 2.5 kilometers deep, and they wait there in the perpetual cold and the perpetual darkness, as patient as the ice itself, watching for events that might occur only a handful of times in the course of a year, or even less frequently than that. The ice at these depths is so old and so pure and so free from air bubbles that it is almost perfectly transparent, a natural medium through which light can travel remarkable distances without being scattered or absorbed. And this is precisely why it was chosen. Because when a neutrino of sufficiently high energy happens to interact with an atom within this ice, the collision produces other particles that travel faster than light can move through ice. And in doing so, they create a cone of blue radiation called Cherenkov light, a glow that spreads outward through the frozen water like a sonic boom spreads through air. It is this faint blue glow that the sensors detect, recording the precise timing and intensity of the light at each module along the strings. And from these measurements, scientists can reconstruct the direction from which the neutrino arrived and estimate how much energy it carried. The process is not unlike listening for a whisper in a silent room, except that the room is a cubic kilometer in volume, and the whisper might come only once in many months. And yet, the patience of the instrument is rewarded, because the ice is always watching, the sensors are always recording, and the data flows continuously to computers on the surface and then outward through satellite links to research institutions around the world. In the year 2017, this patience yielded a discovery of profound significance. When the IceCube detector registered the arrival of a high-energy neutrino that stood out from the usual background of lower-energy particles that pass through the ice in steady numbers. This particular neutrino arrived on the 22nd of September, and it carried an energy of approximately 290 tera-electron volts, a quantity difficult to comprehend in everyday terms, but sufficient to say that it represented an extraordinary concentration of energy within a single particle, energy that spoke of violent origins in some distant and powerful source. The scientists who analyzed the detection were able to determine the direction from which it had come with reasonable precision, and within minutes of the event being flagged by automated systems, alerts were sent to observatories around the world, a coordinated effort to turn telescopes of every kind toward that particular patch of sky. What they found there was a blazar, a type of active galactic nucleus powered by a supermassive black hole at the center of a distant galaxy. A black hole that is actively consuming matter and in the process generating jets of particles and radiation that stream outward at nearly the speed of light. This particular blazar is catalogued as TXS 0566 plus 0566 plus 056, and it lies approximately 4 billion light-years from Earth, a distance so immense that the light we see from it today, and the neutrino that arrived in September of 2017, began their journeys when the Earth was still in the early stages of its formation, when the solar system was young and the continents of our world had not yet taken their present shapes. For 4 billion years, this neutrino traveled through the expanding universe, passing through the vast emptiness between galaxies, through the halos of dark matter that surround galactic clusters, through the diffuse gas and dust of intergalactic space. And through all of this journey, it interacted with essentially nothing, because neutrinos are so reluctant to engage with ordinary matter that the universe to them is almost entirely transparent, a great empty darkness through which they glide without resistance. And then, after this unimaginable journey, after crossing a significant fraction of the observable universe, this particular neutrino happened to strike an oxygen atom in the Antarctic ice, and in that collision, it created a shower of particles that radiated blue light. And that light was caught by the sensors that had been placed there precisely in the hope of witnessing such an event. The identification of TXS 0566 plus 0566 as the source of this neutrino marked the first time that scientists could definitively point to a specific object beyond our own galaxy and say with confidence that it had produced a high-energy neutrino that we detected here on Earth. It was a moment comparable to the first time astronomers turned a new kind of telescope toward the sky, because it represented the opening of an entirely new way of observing the universe, a new sense through which we could perceive phenomena that had previously been invisible to us. But the ice cube detection, as significant as it was not the first time that neutrinos had carried messages to us from beyond our solar system. 30 years earlier, in the winter of 1987, a different kind of cosmic event had already demonstrated the extraordinary potential of neutrino astronomy, and it had done so in a way that confirmed some of the most important theories about how massive stars end their lives. On the 23rd of February of that year, 3 neutrino detectors located at different points around the Earth simultaneously registered an unusual burst of activity, a sudden flurry of detections that lasted only about 13 seconds, but that represented, within that brief window, an unmistakable signal from the cosmos. The detectors were the Kamiokande 2 instrument in Japan, the Irvine, Michigan Brookhaven detector, known as IMB, located in a salt mine beneath Lake Erie in Ohio, and the Baksan Neutrino Observatory in the Caucasus Mountains of Russia. And all 3 of them, despite being separated by thousands of kilometers and operated by independent teams of scientists, recorded their excessive neutrino events within the same narrow span of time. In total, approximately 25 neutrinos were detected across these 3 facilities during that brief burst, a number that might seem insignificant until one considers how rarely these instruments detect any neutrinos at all, and how remarkable it is that multiple facilities should all observe an excess at the same moment. The source of these neutrinos, it would soon become clear, was a supernova in the Large Magellanic Cloud, a small satellite galaxy that orbits our own Milky Way at a distance of approximately 168,000 light-years. This supernova, designated SN 1987A, was the closest stellar explosion observed since the invention of the telescope, and it provided astronomers with an unprecedented opportunity to study the death of a massive star in detail. But what made the neutrino detections particularly significant was not simply that they coincided with the supernova, but that they arrived before the light did. The optical brightening of SN 1987A was first observed several hours after the neutrino burst was recorded, and this timing was precisely what theoretical models had predicted. When a massive star exhausts the nuclear fuel in its core and can no longer support itself against the inward pull of gravity, the core collapses with tremendous speed. And in that collapse, the density and temperature rise to such extreme values that protons and electrons are forced together to form neutrons. And in each such interaction, a neutrino is released. The number of neutrinos produced in this process is almost beyond comprehension, as the entire core of the star is converted into a dense ball of neutrons within a fraction of a second. And the energy carried away by these neutrinos is greater than the total energy the star has radiated as light over its entire lifetime of millions of years. These neutrinos stream outward from the collapsing core at nearly the speed of light, escaping immediately because even the incredibly dense matter of the collapsing star is essentially transparent to them, while the shock wave that will eventually blow the outer layers of the star into space, creating the brilliant optical display we call a supernova, must fight its way outward through the overlying material, a process that takes several hours. And so the neutrinos arrive first, carrying news of the core collapse before the light that follows. And this is precisely what was observed on that February day in 1987. The 25 neutrinos that were detected represented only a vanishingly small fraction of the total number that passed through the Earth during those seconds. For we must remember that trillions upon trillions of neutrinos from SN 1987A streamed through our planet, and nearly all of them continued onward into space without interacting at all. But those few that did interact, those 24 particles that happened to strike atoms within the water or scintillator fluid of our detectors, were enough to confirm decades of theoretical work about how stars die, and to open a new window onto one of the most violent and fundamental processes in the universe. Those neutrinos had traveled for 168,000 years to reach the Earth, having begun their journey at a time when modern humans had not yet spread beyond the African continent, when the glaciers of the ice ages advanced and retreated across the northern lands, when the entire history of human civilization lay far in the future. They traveled through the space between the Large Magellanic Cloud and the Milky Way, through the outer reaches of our own galaxy, past countless stars and planetary systems, and finally through our solar system to reach the small blue planet where instruments had been prepared, almost by chance, to receive them. And for all of that immense journey, for all those thousands upon thousands of years, they interacted with nothing, passing through matter as if it did not exist, until at last a handful of them happened to transfer their energy to atoms within our detectors, creating the signals that would be recorded and analyzed and celebrated as one of the great achievements of observational astrophysics. Neutrino astronomy, as it has come to be called, represents something genuinely new in our relationship with the cosmos, a way of sensing and understanding the universe that is fundamentally different from everything that came before. For nearly all of human history, and indeed for most of the history of modern astronomy, our knowledge of the universe beyond Earth came to us through light, through electromagnetic radiation of various wavelengths, from radio waves to gamma rays. Light is how we see the stars and the galaxies, how we map the structure of the cosmos, how we measure the expansion of the universe and the properties of distant objects. But light can be blocked and absorbed and scattered, and there are processes in the universe, deep within the cores of stars and at the hearts of violent cosmic events, that are hidden from light, shrouded in matter that is opaque to electromagnetic radiation. Neutrinos pass through this matter without hesitation, emerging from the very centers of these events and carrying with them information about conditions that no other messenger can reveal. To detect neutrinos from a supernova or a blazar or any other cosmic source is to see the universe through an entirely new sense, to perceive processes and phenomena that would otherwise remain forever invisible. To us, hidden behind curtains of matter that block every photon but cannot hinder the passage of these ghostly particles. And so we come now to consider something rather wonderful, in the quietest possible way, which is the question of why these particles, these neutrinos that fill every corner of space and stream through your body in such unimaginable numbers, leave no trace of their passage whatsoever, no warmth, no pressure, no faint electrical tingle, nothing at all that your nervous system or any of your senses could ever detect. And the answer lies in understanding what neutrinos lack, which turns out to be almost everything that ordinary matter possesses. And it is precisely this absence, this profound lightness, that makes them the ghosts they are. You see, the atoms that make up your body, and the chair beneath you, and the walls of the room where you are resting, are held together and interact with one another through forces that have certain ranges and certain strengths. And the most familiar of these forces is electromagnetism, which is responsible for nearly everything you experience in daily life. The solidity of objects, the light that reaches your eyes, the warmth of a fire, the gentle resistance when you press your hand against a table, all of this emerges from the electromagnetic force, which acts between particles that carry electric charge. And the remarkable thing about electromagnetism is that it has infinite range, meaning that two charged particles can, in principle, influence one another across any distance whatsoever. Though of course the strength of that influence fades with distance according to well-known mathematical laws. Now, electrons carry electric charge, and protons carry electric charge, and this is why atoms behave the way they do, binding together into molecules, forming the substances that make up your world. But neutrinos, and here is the essential point, carry no electric charge at all, not even the smallest fraction of a charge. And this means that the electromagnetic force, which governs so much of what you see and touch and feel, simply does not apply to them. They are invisible to it entirely, as if they existed in a separate realm that overlaps with ours in space, but not in interaction. And so, when a neutrino passes through an electron, or comes near a proton. There is no electromagnetic push or pull, no deflection, no scattering, nothing at all from that particular force. But electromagnetism is not the only force in nature, and you might wonder whether some other force could step in and cause neutrinos to interact with the matter they pass through. And indeed, there is such a force. It is called the weak nuclear force, or simply the weak force. And it is through this force alone that neutrinos can interact with other particles. But the weak force has a very particular character that makes such interactions extraordinarily rare. And to understand this character, we need to think about distance, about the unimaginably tiny scales at which particles exist. The weak force operates only at distances smaller than approximately 10 to the power of -18 meters, which is to say, 1/1000th of a billionth of a meter, or roughly 1,000th the diameter of a proton, and this is so small that it is difficult to convey with any everyday comparison. But perhaps you might picture it this way. If a proton were enlarged to the size of a city, the weak force would only act across a distance equivalent to a small fraction of a single grain of sand somewhere in that city. And so, for a neutrino to interact with any particle through the weak force, it must approach that particle to within this almost impossibly tiny distance. And even then, even when this happens, the weak force is, as its name suggests, weak, much weaker than electromagnetism or the strong force that holds the nucleus together. And so the probability of an interaction occurring, even at these close approaches, remains vanishingly small. This combination of having no electric charge and interacting only through a short range, feeble force is what gives neutrinos their ghostly nature, and it is why, when the trillions upon trillions of neutrinos pass through your body each second, essentially none of them are stopped, or deflected, or absorbed. They simply continue on their way as if you were not there, as if all the atoms of your body, with all their protons and neutrons and electrons, were nothing more than empty space. And in a sense this is true, because at the scales relevant to the weak force, matter is almost entirely empty. The distances between particles are vast compared to the tiny region where the weak force can act. And so a neutrino sailing through your body is like a small bird flying through a sparse forest where the trees are separated by miles. The chance of striking any trunk is negligible. There is another quality of neutrinos that contributes to this phantom existence, and that is their mass, or rather, their almost complete absence of mass. For neutrinos are among the lightest particles known to exist, so light that for many decades after their prediction, scientists believed they might have no mass at all, that they might be truly massless like photons, but we now know that neutrinos do possess some small amount of mass. The evidence coming from the phenomenon of neutrino oscillation that we have spoken of before, where neutrinos change their type as they travel, a behavior that is only possible if they have mass. However, we have not yet been able to measure this mass directly, only to place upper limits on how large it might be. The most stringent of these limits comes from the K-Reen experiment, which is located in the town of Karlsruhe, in the southwestern part of Germany, where a collaboration of scientists has constructed an enormous and extraordinarily precise instrument designed specifically to weigh neutrinos, though not in any ordinary sense of the word weighing. For one, cannot place a neutrino on a scale, and so the experiment takes a more indirect approach, studying the radioactive decay of tritium, which is a heavy form of hydrogen, and examining the energy spectrum of the electrons emitted during this decay. Because the tiny mass of the neutrino affects the maximum energy that these electrons can carry, and by measuring this effect with sufficient precision, the mass of the neutrino can be inferred. The centerpiece of the Ka-trine experiment is a spectrometer that weighs 200 tons and stretches approximately 23 meters in length. And this spectrometer is so sensitive that it must be kept in an extraordinarily high vacuum, among the best vacuums ever achieved on Earth, to prevent stray air molecules from interfering with the measurements, and the entire apparatus was so large that transporting it to Karlsruhe required a specially planned journey by ship and barge and road, taking months to complete. And all of this effort, all of this precision engineering, is directed at measuring something incredibly tiny, the mass of a particle that is so light it barely registers. As of the most recent measurements, the Ka-trine collaboration has established that the mass of the neutrino cannot exceed approximately 0.8 electron volts, which is a unit of mass that particle physicists use, equivalent to an almost incomprehensibly small number of grams. And to put this in perspective, an electron, which is itself a very light particle, has a mass of about 511,000 electron volts, which means that neutrinos are at least 500,000 times lighter than electrons, and electrons themselves are already about 1,836 times lighter than protons. So we are speaking here of particles that are lighter than light, if one may use such a phrase. Particles that carry so little mass that the very concept of weight seems almost inapplicable to them. And yet, this tiny mass, whatever its precise value turns out to be, has profound consequences for the nature of the universe. Because neutrinos are so numerous that even their infinitesimal mass adds up, contributing to the total mass of the cosmos in a way that affects how galaxies form and how the large-scale structure of the universe evolves over time. And so cosmologists are keenly interested in determining the exact mass of neutrinos, not merely as a matter of particle physics curiosity, but because it tells us something about the shape and fate of everything we can see. There is something philosophically striking about all of this, something that perhaps settles gently into the mind as the body relaxes and the thoughts grow quieter. And it is this, that most of the particle traffic in the universe is invisible to us. Most of what is happening at the subatomic level goes entirely unnoticed by the ordinary matter that makes up our bodies and our instruments. We are immersed in a sea of neutrinos that pass through us continuously, and we have no awareness of this whatsoever. Our senses evolved to detect light and sound and pressure and temperature, all of which arise from electromagnetic interactions. But the weak force through which neutrinos operate leaves no mark on our experience. And so there is this entire dimension of physical activity, this constant passage of particles through every point in space, that exists beyond the threshold of perception. Some of the neutrinos passing through you at this moment were born in the heart of the Sun, created just 8 minutes ago during the nuclear fusion that powers our star. And they carry energies of a few million electron volts, moving at speeds so close to the speed of light that the difference is negligible. But there are other neutrinos, far more ancient, that have been traveling through the universe since the very beginning, since approximately 1 second after the Big Bang, when the universe had cooled sufficiently for neutrinos to stop interacting with other matter and begin their long, solitary journeys through expanding space. These ancient neutrinos are called cosmic background neutrinos, or relic neutrinos, and they fill the universe with a density of approximately 336 per cubic centimeter, which is roughly similar to the density of cosmic microwave background photons, those ancient light particles that also date from the early universe and form a faint glow detectable by radio telescopes. But while the cosmic microwave background has been studied extensively and mapped in exquisite detail, the cosmic neutrino background has never been directly detected. Because these relic neutrinos have cooled over the 13.8 billion years of cosmic expansion to temperatures of less than 2 degrees above absolute zero, which means they are moving very slowly by neutrino standards, with energies far below those of solar neutrinos, and their already tiny interaction probability becomes tinier still. These cold, slow, ancient neutrinos are passing through your body at this moment, relics of an era when the universe was less than a second old, when everything that would become the stars and galaxies and planets, and eventually you, was compressed into a state of unimaginable density and temperature. And now these particles drift quietly through the cosmos, through your bedroom walls and through your resting body, carrying with them information about the earliest moments of creation, information that we have not yet found a way to read, though experiments are being planned and theories developed that might one day allow us to detect even these ghostly messengers. And perhaps it is comforting to know, or perhaps it is simply interesting in a quiet way that suits this drowsy hour, that despite all this invisibility, despite the fact that you can never feel a neutrino, some neutrinos do interact with the atoms of your body, not often, not in any way you could notice, but over the course of an entire human lifetime. The mathematics tells us that a few dozen atoms somewhere within you will be struck by neutrinos, a few dozen collisions in all those decades of living. Out of the trillions of particles passing through you every second of every day, which gives some sense of just how improbable these interactions are. And yet, they happen, rarely, quietly, without fanfare. A nucleus here or there absorbing a neutrino and transmuting into something slightly different. A tiny change in a single atom among the trillions of trillions that compose your being. You will never know which atoms were struck. You will never feel the moment of impact. There will be no signal, no sensation, no record in your memory. And this is perhaps the deepest lesson of the neutrino, that the universe contains so much activity, so much motion and interaction and physics that exists entirely below the threshold of our awareness. And yet it is real. It is happening. Right now, as you lie there growing drowsy, the weak force is mediating its rare events. The spectrometer in Karlsruhe is measuring its electrons. The cosmic background neutrinos are drifting past at walking pace, and the sun continues to pour out its enormous flux of particles that pass through the night side of the Earth and through your body and onward into space. And none of this disturbs your rest. None of this adds any weight to your eyelids or any warmth to your skin, for neutrinos are the lightest of passengers, barely present, almost nothing, And their profound lightness of being is what allows them to travel from the heart of a star, or from the birth of the universe itself, to wherever you are now, arriving unchanged, unimpeded, unnoticed, as though all the matter in between were merely a dream of solidity. And perhaps, in a way, that is what it is. And so we come now to the widest view of all, the perspective that stretches not merely across space, but across the entirety of time itself, back to the very beginning of everything. And we find that even here, especially here, the neutrino has been present, drifting through the ages in numbers beyond all counting. And some of those ancient travelers, those particles born in the first moments of existence, are passing through you at this very moment, connecting your quiet evening to the birth of the cosmos in a way that is both literally true and gently astonishing. Let us begin at the beginning. Or rather, let us begin approximately 1 second after the beginning, because in those first fleeting moments, the universe was so impossibly hot and dense that even neutrinos, those most ethereal of particles, could not travel freely, and they bounced and scattered and interacted with the seething plasma of the primordial cosmos moss, trapped in a kind of cosmic fog alongside everything else. And the temperature in those moments was measured not in thousands or millions, but in billions of degrees. A heat so profound that matter as we know it could not yet exist. And particles of all kinds emerged and annihilated in constant furious exchange. And neutrinos were created in staggering abundance during this epoch. And they have been traveling ever since. When the universe was approximately 1 second old, something remarkable happened. Though perhaps remarkable is not quite the right word for an event so quiet and so fundamental. And what happened was simply that the universe had expanded and cooled enough that neutrinos could finally slip free, their interactions with other matter becoming so rare that they effectively stopped altogether. And from that moment forward, those neutrinos have been traveling in straight lines through the cosmos, undisturbed and undisturbing, carrying with them a kind of frozen memory of conditions that existed when everything was new. These ancient neutrinos, known as the cosmic neutrino background, fill all of space, and they are everywhere in approximately equal numbers. And the calculations suggest that there are about 330 of them in every cubic centimeter of the universe, which means that in the volume of your bedroom, in the space where you rest tonight, there are trillions upon trillions of these primordial particles, and they have been traveling for 13.8 billion years to reach this moment, this place, your gentle presence here in the quiet dark. It is worth pausing to consider what this means, to let the thought settle slowly like dust in still air, because these neutrinos were created before any star had ever formed, before any galaxy had begun to coalesce, before the cosmic web of structure had even begun to take shape. And they carry information about an epoch that is otherwise almost entirely hidden from us, because ordinary light, the photons of the cosmic microwave background radiation that astronomers study with such care, those photons were released when the universe was already 380,000 years old, an eternity compared to the single second at which the neutrinos went free. And so the cosmic neutrino background represents a window into an earlier and more mysterious time. And yet, we cannot easily detect these ancient neutrinos. because their long journey through the expanding universe has cooled them to temperatures far below anything we can achieve in our laboratories. And they now move with such little energy that their already vanishingly small interaction probability has become smaller still, and current experiments cannot see them, though physicists dream of future technologies that might one day reveal this fossil radiation, this ghost of the universe's infancy. And until then, we simply accept their presence on the strength of our calculations, our theories confirmed by so many other observations that we trust them even in this realm beyond our direct perception. But the cosmic neutrino background is not the only source of ancient travelers passing through your body tonight. Because every star that has ever burned in the history of the universe has produced neutrinos in its core. And many of those stars burned brightly and then faded long before our solar system had even begun to form from its cloud of gas and dust. And the neutrinos from those ancient suns, from stellar generations that rose and fell in distant galaxies billions of years ago, those particles are still traveling, still streaming through the cosmos, and some fraction of them, some infinitesimally small but non-zero portion, are passing through this moment, through this place, through you. Consider the supernovae, those catastrophic stellar deaths that briefly outshine entire galaxies, and in a single such explosion, lasting mere seconds of intense neutrino production, a dying star releases more neutrinos than our Sun will produce in its entire 10 billion year lifetime. And there have been countless supernovae across the history of the cosmos, in our galaxy and in others, in galaxies so distant that their light has not yet reached us or will never reach us, because the expansion of space carries them beyond our horizon. And the neutrinos from all of these events are traveling still, spreading outward in all directions, filling the universe with an ever-increasing population of these ghostly messengers. And some of them are here now, passing through your walls, your ceiling, your chest, rising and falling with each peaceful breath. There is something deeply calming about this image, something that connects your small and precious life to the vastness of cosmic history. Because you are not separate from the universe, you are not isolated on this small world. You are instead continuously traversed by particles that have traveled across billions of light years and billions of years. And they pass through you without harm, without disturbance, carrying their ancient stories onward to whatever distant destination they will never quite reach. And you are part of their journey for one infinitely brief moment. And then they are gone, and others take their place. And the stream continues, as it has continued since the beginning, as it will continue until the end. And now, let us turn to the present, or rather, to the very recent past and the near future, because physicists around the world are engaged in careful experiments designed to understand neutrinos more deeply. And some of these experiments are searching for clues to one of the greatest mysteries in all of physics, the question of why there is something rather than nothing, the puzzle of matter and antimatter and their curious asymmetry. In the first moments of the universe, according to our best understanding, matter and antimatter should have been created in precisely equal amounts. And when matter and antimatter meet, they annihilate completely, converting their mass into pure energy. And so, if the amounts were truly equal, then everything should have cancelled out. Every proton meeting an antiproton, every electron meeting a positron, leaving nothing behind but radiation. No atoms, no stars, no galaxies, no worlds, no life. No, you lying here in the soft darkness, listening to these words. And yet here we are. And the universe is filled with matter and almost entirely empty of antimatter. Which means that something must have tipped the balance. Some subtle difference between matter and antimatter that allowed a small excess of matter to survive the great annihilation. Perhaps 1 part in a billion. And that 1 part in a billion is everything we see and know and are. Neutrinos may hold the key to this mystery, because physicists have discovered that neutrinos can oscillate between their different types, transforming from electron neutrinos to muon neutrinos to tau neutrinos as they travel. And the question now being investigated is whether neutrinos and antineutrinos oscillate in exactly the same way, or whether there is a subtle difference, a violation of the symmetry known as CP symmetry, and if such a violation exists in the neutrino sector. If neutrinos and antineutrinos behave even slightly differently, then this could help explain how matter came to dominate, how existence itself came to be. In Japan, nestled among forested mountains, there is an experiment called T2K, which creates beams of neutrinos at a facility called J-Park on the eastern coast and sends them 295 kilometers through the Earth to the Super Kamiokande detector. And by studying how these neutrinos oscillate during their journey, physicists are searching for hints of CP violation, comparing the behavior of neutrino beams with antineutrino beams, looking for the tiny asymmetry that might explain our existence. And in the United States, spanning the distance from Illinois to Minnesota, there is the NOVA experiment, which similarly sends beams of neutrinos through 810 kilometers of earth and rock, from Fermilab near Chicago to a detector in Ash River, Minnesota, near the Canadian border, and NOVA, too, is searching for CP violation, gathering data year after year, event by event, building up the statistics needed to answer questions of cosmic significance with patient and meticulous care. The results so far are tantalizing, which is to say that there are hints, suggestions, preliminary indications that CP violation in the neutrino sector may indeed exist, but the measurements are not yet precise enough to be certain. And so the work continues, and new experiments are being planned and constructed, larger and more sensitive than anything that has come before. In Japan, construction is underway on Hyper Kamiokande, a successor to the Super Kamiokande detector that has served neutrino physics so well for so many years. And Hyper Kamiokande will be immense, a cylindrical cavern carved deep within Mount Nijigo in Gifu Prefecture, and it will be filled with 260,000 metric tons of ultra-pure water, making it about 8 times larger than its predecessor, and its walls will be lined with approximately 40,000 photomultiplier tubes, each one waiting in the darkness for the faint flash of light that signals a neutrino interaction. And when it begins operation later this decade, it will gather data at a rate far exceeding anything currently possible. And it will help answer questions that have puzzled physicists for generations. And in the United States, in the former Homestake gold mine in Lead, South Dakota, now known as the Sanford Underground Research Facility, another great experiment is taking shape, and it is called DUNE, the Deep Underground Neutrino Experiment, And it will use a different detection technology. Great volumes of liquid argon cooled to -186 degrees Celsius. And it will receive beams of neutrinos sent 1,200 kilometers through the Earth from Fermilab. And the combination of this long baseline and the precision of liquid argon detection will allow Dune to study neutrino oscillations with unprecedented accuracy, probing CP violation, determining which neutrino mass state is heaviest, and perhaps even detecting neutrinos from a supernova occurring in our galaxy, should one occur during the experiment's lifetime. These experiments represent decades of planning and construction, the work of thousands of physicists and engineers from countries around the world, collaborating across borders and across time zones, united by the shared desire to understand, to know, to unravel the mysteries that neutrinos carry with them from the heart of the Sun and the depths of the cosmos. And while these great scientific endeavors proceed, while data is gathered and analyzed and discussed at conferences in Geneva and Tokyo and Chicago, you are here, resting quietly. And the neutrinos do not wait for our understanding. They simply are. They simply travel. And they pass through you now as they have passed through every living thing that has ever existed. Through the dinosaurs and the trilobites and the first single-celled organisms that stirred in ancient seas. Through your ancestors in all their varied forms. Through every generation that has slept beneath the stars. Let your body sink deeper into rest now, feeling perhaps the weight of blankets, the softness of pillow, the gentle rise and fall of your own breathing. And know that in this moment you are being traversed by messengers from the beginning of time, particles that have traveled since the universe was 1 second old. Neutrinos born in stars that burned out before our galaxy had fully formed, travelers from supernovae that exploded in the cosmic dawn, and they pass through you without the slightest resistance, without disturbing a single atom of your being. And they continue onward, carrying their ancient momentum into the endless future. You are unharmed, utterly untouched, and you will wake tomorrow with no trace of this cosmic passage, no evidence that 100 trillion travelers moved through your body in every second of the night. And this is perhaps the most remarkable thing of all, that the universe can be so full of motion and yet so gentle, so teeming with particles and yet so perfectly quiet, so ancient and vast and yet so willing to let you rest undisturbed. Picture yourself now as a point of stillness in a great flowing river, except that the river passes through you rather than around you. And the water is made of neutrinos, countless beyond counting, and they have been flowing since the beginning, and they will flow until the end. And you are part of this flow for the brief moment of your life, connected to every star that ever burned, to every supernova that ever flared, to the first second of existence itself. And yet you need do nothing. You need understand nothing. You need only rest here in the gentle dark while the cosmos continues its endless journey through your peaceful form. The stars above you, hidden perhaps by ceiling and cloud, are even now producing the neutrinos of today, and these will travel outward to become the ancient neutrinos of some impossibly distant future. And beings we cannot imagine may one day be traversed by particles born in our familiar sun. And so the stream continues, connecting past to present to future in an unbroken flow, and you are part of it. A brief eddy in the current, a momentary presence in the infinite drift. Sleep now, if sleep will come, and let the universe flow through you, ancient and silent and kind, connecting you to the beginning of time, to the vast and gentle mystery of existence itself, to every point of light in the endless dark. And know that you are held in something far larger than yourself, traversed but never troubled, visited by travelers who ask nothing and take nothing and leave no trace. Only the softest whisper of connection to everything that ever was and everything that will ever be.